Hi, this is an example problem from Chapter 16 on traveling waves. Pause for a moment and read the problem. So we have a graph here that shows two traveling waves, and they're transverse waves because the oscillation, look at the red one for example, is up and down. Meanwhile, the wave is traveling off towards the right, which is transverse or perpendicular to the oscillation of the medium up and down. Now, we should think of this as maybe like a rope, a wave on a rope or something, where the red object is the rope itself. And each little wave pulse here is moving along, the entire wave is moving along to the right at a speed of 10 meters per second. And on the graph, we've essentially plotted here along the y-axis one direction, that's the transverse displacement of the rope. On the x-axis, we also see where the rope is located. In this problem, we're going to go ahead and solve some of the key characteristic properties of a wave just by looking at the picture of the wave, the graph of the wave in space. And we're going to do it for the blue and for the red waves, two different waves. We're going to look for the amplitude, the wavelength, and the frequency. So what we can do here is just by looking at these waves, let me start by doing the red wave first. So right down over here, red, and the amplitude. Well, the amplitude is the furthest that a segment of the medium ever gets from the origin. So here's the very highest that you ever get. Here is the 0 line, and so the amplitude for the red wave, it's going to be equal to 0.5 meters, just by inspection of the graph. Now for part B, for the red wave, what's the wavelength? That is the distance of one complete oscillation through space, a distance of space. And so one way to look at that is go from peak to peak. So there's one peak. There's another peak, and the distance between that is the wavelength. And we can see that in this case, this is 2 meters for the red wave. Let's put R here for red. For part C, we're asked to calculate the frequency. Now, this is ordinary frequency F, which we measure in hertz. If it was angular frequency, it would be radians per second, and the variable would be omega. But we have a basic equation that relates speed, frequency, and wavelength for any type of wave. And that really important general fundamental equation is this. The wave speed is equal to the wavelength times the frequency. And we want to solve for the frequency, which means we're going to go ahead and take the wave speed and divide by the wavelength. In this problem, the speed is 10 meters per second, and the wavelength is equal to 2 meters for the red wave, which gives us a frequency here. We're going to cancel out the meters, and we're going to end up with 5 per second, which of course is the same as 5 hertz. 1 over second is a hertz. Let's do the same thing for the blue wave here. So the amplitude for the blue, the wavelength for the blue, and finally we're going to calculate the frequency for the blue. This is for the red. And again, that's going to be speed of the wave divided by the wavelength. So for the blue one, again, let's go ahead and take a look at it. We have got a amplitude here, 0.25 meters. We have a wavelength, peak to peak, or you can go trough to trough, doesn't matter. Oops, that's not the blue one. Peak to peak. There we go. Lambda blue, that looks like that is going to be equal to, this is 1 meter here, and we've got 1, 2, 3, 4 of those, so 4 meters for the blue wave. And if we calculate the frequency of the blue wave, that's again same speed, 10 meters per second, divided by 4 meters. Cancel the meters out again. 1 over seconds will be hertz, and we get an answer of 2.5 hertz for the blue wave. All right, let's look at part D here. D, E, and F. Consider a particle of the wave medium attached to the blue wave. Calculate the magnitude of the particle's maximum displacement, velocity, and acceleration. So in this case, what we're doing is we're looking at these waves and consider a little particle that is located on the wave. So let me draw something here on the blue wave. There's a little piece there, little segment of medium. A segment of the medium that's oscillating. This might be a piece of the rope if this is a wave on a rope. What's this do? It's going to go up and down between the maximum amplitudes, 0.25 meters minus 0.25 meters. In fact, it undergoes simple harmonic motion. Each little segment of the wave oscillates up and down along the y-axis, undergoing simple harmonic motion. In fact, we can look at the equations of motion for the particle in a wave. They are the simple harmonic equations of motion that we learned in chapter 10. The same period and frequency relations hold. And notice that omega we have written here inside the cosine and sine argument. So we're going to go ahead and use our value of frequency and calculate omega. And to get the maximum values of these, just as in chapter 10, well, it's the amplitude. It's a omega for the velocity. It's a omega squared for the acceleration. So let's go ahead and look at that real quick. All right, so as we saw for part D, to get the maximum amount of the displacement, that's going to be equal to the amplitude. Well, we already saw for that. For the blue wave, that's equal to 0.25 meters. Now to get the maximum magnitude of the velocity, the particle for the blue wave, and this is our maximum here. That, as we saw, it's just going to be omega times a. And for the acceleration of the particle for the blue wave, maximum, as we saw, it's going to be omega squared times a. So let's just calculate omega for the blue wave. Omega is equal to 2 pi times the ordinary frequency. We have 2 pi times 2.5, 1 per second, which gives us 5 radians per second. We just add the radians there because it's angular frequency. And now we can go ahead and solve these. So we've got 5 rad per second times the magnitude 0.25 meters, and for the acceleration we have 5 rads per second squared times the amplitude 0.25 meters. We're going to cancel out rads because we're multiplying by meters, and when we get this, we'll get some answers here for the velocity. Oops, I realized I forgot to put pi inside here, so let's go ahead and put pi inside there. Now that I've fixed the angular frequency to the correct value, this comes out to a max velocity of 3.93 meters per second and a maximum magnitude of acceleration 19.6 meters per second squared. Oops.